Okay, so last time we got started with this list. I'm just going to keep going with that. Before I start with that, remember the exam is on Monday. Um, and everything, all the daily problems are, eligible to be reflected on the test up through those first two questions on um, rigid body statics. Okay, yes, correct. Yeah. Okay, so remember the test.
And like basically we need to do some problems. That should be it, or
The test, yeah, it's just going to be probably four questions, four problems, that kind of thing. Yep. And remember to bring a calculator.
and it'll have like momentum.
What?
It will have momentum.
Oh, moment.
Moment.
Yes, that will be on there because it's in those first two. Yeah. Okay, so last time I started talking, just going through this list, I'm just going to jump back to my notes from last time so you don't have to write this down again. But remember, I just introduced, I called it joint category 1. It's the two types of joints that introduce a single variable into Newton's laws. They do that by applying a force with a known direction but an unknown magnitude. And I just wanted to show you one thing about, so there are two of these. One is a frictionless contact and one is a pin and slot. So I have a pin and slot joint here, and I want you to sort of think about how this works. So this is pretty little, but the slot is aligned with the slot on the picture, and the arm is aligned with the arm in the picture. Okay. And remember that I said before we started, when you're trying to think of what loads a joint applies to a body, think of what degrees of freedom are eliminated by the joint, not the ones that are allowed. It's very easy for your brain to go think about the ones that are allowed by the joint, but think about the ones that aren't allowed. So in this case, let's think about what the arm can do. Okay. Remember, there's 3 degrees of freedom. There's 2 translational components, and then there's 1 rotation. So one by one, let's think about what's allowed. So, okay, I'm going to think of an axis that's along the slot. Is it allowed to translate along the slot by this joint? Yes. And so that means that there's no force component along that slot. Okay. What about perpendicular to the slot? I'm trying to do it and it won't go. The slot's preventing it from doing that. And so there's a force component perpendicular to the slot. Okay. And now think about rotation. I can rotate the arm, so there's no couple applied by the joint. And so that's the end of it. All there was a single force with a known direction perpendicular to the slot, and that's what we have written down.
At the end of the slots.
Yeah, so we're not, since it's statics, we don't have to worry about that.
We're just assuming that it goes on the slot.
Well, yeah, because it's static, so it's just staying in place. So all we care about is the millimeter to each side, you know.
So not like a long slot, just in that one position in this slot.
Yeah.
Yeah. Yep, Professor. So if this pin and slot isn't perpendicular, wouldn't that mean that any force like this would also mean a force like that?
You mean in relation to the coordinate system?
And yeah, in relation to like the slot itself, like wouldn't that mean that there needs to be a force, and that the pin needs to be moving or accelerating?
Oh, well, no, because so this is how you think of the loads that are applied by one joint, but then this body will be constrained by a bunch of joints. Okay, yes, I totally see what you're. So yes, if all that was going on this arm was this thing, then yeah, most likely you'd have to deal with dynamics. But the idea in statics is that there's also a cable connected to it. There's all these things that keep it from moving. This is only one of those things. But you treat the joints like they're the only thing going on to figure out at each joint what loads are applied.
Okay, thanks.
Okay, so let's go back to today, and now we're going to get into joint category 2. Okay, so if joint category 1 restricted 1 degree of freedom, put 1 variable into the equations, Newton's laws equations, and now we're going to do 2. How many total joint categories are there going to be in 2D? 3, yep, that's perfect. There's only 3 degrees of freedom. That's all you can restrict. So there's going to be a lot more categories. There's going to be 6 categories when we start doing 3-dimensional joints. Okay, so joint category 2. So these are joints that apply a force with an unknown direction. The last one, we knew the direction. Bless you. And so that means that these introduce 2 variables into Newton's laws. And I have 2 of these. The first one is called a pin joint or a hinge. And so this looks like you have one body like that, one body like this, and they can rotate relative to each other around that hinge. I'll call this body 1 and this body 2. A free body diagram of body 1 looks like this. So we'll just follow the rules of a force with an unknown direction. We just draw the 2 vector components in the coordinate system axis directions. And then if I'm using the subscript notation, which is going to be really useful to us, I would write this as the force on 1 by 2. And then a free body diagram of the second body. I would do that the same way. It's a force with an unknown direction. So I would call this the force on 2 by 1. And Newton's third law says the force on 2 by 1 is just negative force on 1 by 2. The reason that that's useful is if we were doing a calculation where we use Newton's laws for both of these 2 bodies, if I had the force here on body 1 called F12 and the force on body 2 called F21, that's 4 variables. And I need 4 equations to solve for that. If you recognize, though, that F21 is equal to negative F12, then you've reduced that to a single variable, and you only need two equations to solve that. Okay, that's the usefulness of that subscript notation for us. Okay, so let's think about it, because I got one of these here too. So here's that hinge that it can move around. So this top body, it starts out with 3 degrees of freedom before you attach it to the joint. Now connected to the joint is its translation restricted horizontally? Yes, so there's a horizontal component. Is it restricted vertically? Yes, so there's a vertical component. Is its rotation restricted? No, so there's no couple, and that's why you get the two components of force. The second type in this category is a friction contact. So let's think of a surface and a body that makes friction contact with it. And so I'll call this body 1 and I'll call this body 2. Then a free body diagram of body 1. Again, has an unknown force vector, so I'll call this the force on 1 by 2. And the free body diagram of body 2. We would call that the force on 2 by 1, and that's equal to negative F12. And then the last category, joint category 3. Well, there's only 3 degrees of freedom available in 2D, so this one has to lock them all up. So this is just some kind of fixed glue weld type joint, you know. The two things can't move relative to each other. So this is usually called a fixed or a weld joint. And so let's think of a beam that's cantilevered out to the right like that. I'll call this body 1 and this body 2. A free body diagram of body 1. Yes?
If it's fixed and neither can move relative to the other, could we treat them in one body?
Yeah, that's a good question. Yes, you certainly can. Sometimes this is a way to calculate the stress that's actually applied on that joint. And so there are times when you would want to do this to see how you needed to fix those two things together. Okay, so there's an unknown force vector. So I'll call that the force on 1 by 2. And then there's an unknown couple, and I'll call that M12. And then if you wanted to do a free body diagram of the thing it's connected to, These would both just be equal and opposite. Yep.
Is there a specific reason why the couple goes counterclockwise?
It has to do with the way cross products work, I guess. That's just saying the same way that I drew the two force components in the positive x and positive y. I'm just going to draw this couple in the direction of the positive couple, which is counterclockwise. Okay, so yeah, don't start doing this as like drawing it the other way and stuff like that. That'll just get confusing when you start getting different signs for it. Just say the default is positive, and if you get a negative answer, that means it's clockwise.
Okay.
Okay, so then the wall, if you isolate a chunk of the wall, you would have a force here of F2, 1, and that's equal to negative F1, 2. And then you would have a couple that would be M2, 1, and that's equal to negative M1, 2. Why does Newton's third law work for couples? We've never talked about doing Newton's third law with moments before. But remember that really a couple is two equal and opposite forces. And so it works for each of those two forces, which has the effect of making it work for a couple for the moment. Yes?
Are there any forces Newton's second law wouldn't apply to?
Newton's third law?
Yeah.
There's no forces. Are there any moments?
Is it a moment
Yeah.
of force?
No, a moment it's its own thing. It's a load, but it's not a force. It's a first moment of a force mathematically. Would you hear all these things with moments in the title, like moment of inertia and all of them, the reason they have that name is that a moment in math is a very specific thing. It's an integral of the thing multiplied by however many terms of so anyways. So it's its own thing, and it takes a distance into account as well as a... All right. So now let's just get to some problems. So now we're finally ready to do real 2D rigid body statics. So the first one, let's say there's a hinge connected to the wall and a big plate connected to the hinge. And we'll say that this length is 0.5 meters and this length is 0.3 meters. And there's a cable connecting this corner to the ceiling. Did I give an angle for that? So let's say that this angle is 45 degrees. And let's say the mass of this thing is 50 kilograms. And we want to calculate the reaction load at the hinge and the tension in the cable. Okay, so I'm going to start with a free body diagram.
Are we assuming that the plate has 90-degree angles?
Yeah. Okay, so there's the free body, the outline. and there's a weight force that's equal, and it acts at the center of the body, the center of mass. And it's 50 times 9.81, so that's 490.5 newtons. We have a hinge joint at the upper left, so you can always just go to this. It's nice. I think it's a good idea. It's good practice to try to remind yourself of what what type of load each joint applies by thinking about the restrictions on the degrees of freedom that it makes. But you can also just go up to the list. This is a pin joint, so we're going to use the rules of a pin joint. You're just trying to turn yourself into like a human lookup list, you know? So this is an unknown force vector. I could call this the force on the plate by the wall or something, but that subscript notation is only useful if then you're going to later isolate the other thing, and we're never going to isolate the wall, so I'm just going to call this R. All it is an unknown force vector. And then we have the cable force, and the rules for a cable force are parallel to the cable, away from the body.
Why is R a moment since it can rotate?
Because that's the thing that we're slowly going to try to get out of. Don't think about the motion that's allowed, think about the motion that's eliminated. So it's a hinge joint, it allows the rotation, and so that means there's no moment. It doesn't allow translation, and so those forces are applied.
Okay, thank you.
Yep. Okay, and now I'm going to fill out the table, row, force, moment. You know, now that we have this, we're back to the questions like the ones you've answered. And so we have to choose an about point. It doesn't matter what point you choose, but I'll choose this one. It'll simplify the math a touch. So first I'll do the force R. What's the row vector for that? 0, yep. And the force is Rx, Ry. Cross product. This times this minus this times this is 0. I'll do the weight next. So the row vector goes from the about point to where the force is applied. So that is 0.25 for X, negative 0.15 for Y. The force is 0, negative 490.5. Cross product is this times this minus this times this.
Where are we saying that the weight force is being?
It acts at the center of mass always. And so for simple shapes like circles and rectangles, it's right in the middle.
Okay.
But pretty soon we'll start doing centroid calculations to calculate the center of mass for more complicated shapes. Okay, so 0.25 times 490.5. So we get negative 122.625. And then the last force is the cable tension. The row vector is 0.50. The force is, that would be T times cosine of 45, T times sine of 45, which is 0.707 T, 0.707 T. The cross product is this times this minus this times this. And so that is positive 0.354, I guess. T.
How do we get 0.77?
Yeah, that is, so our coordinate system is this. The cable force is this. It has a magnitude of T. And this angle is 45 degrees. So so that vector is T times the cosine of 45, T times the sine of 45. Okay. How do I cut this guy? No. Okay, forget it. So now we'll go to Newton's second law. And that says just add up all those forces and set them equal to 0. So Rx, Ry plus 0, negative 490.5. Plus 0.707 T, 0.707 T is equal to zeros. And then the moment equation, rotational Newton's second law, says negative 122.625 plus 0.354 T is equal to 0. And so you could do reduced row echelon form here, just solve it by substitution.
We only have two equations.
Yeah, the one, that's right.
We need one more because we have Rx, Ry, and T.
No, we have 3 equations. The vector equation is 2 equations. There's the x and the y. So from this, you get the T is equal to 346.40. That's positive, which is good for a cable tension. If you got a negative, something went wrong. And then the R force is equal to the x component is negative 244.90. And the y component is positive 245.60. Any questions about that? Okay. Let's do another one. So let's say we have a pin joint on this side and a beam. And a roller at the midpoint. And let's say that the whole length is 2 meters. And we have a force of 300 newtons that's applied at a 30-degree angle to the end. And let's say that the mass of this thing is 20 kilograms. And again, we want to calculate those reaction loads at the joints. So free body diagram.
But you say reactions of the joints.
Mhm.
What does that mean?
That means the loads that the joints apply to the body.
So like they'll know.
Yeah, exactly. They're either forces or couples, depending on the type of joint it is.
Okay.
So, okay, we have the 300. We have the weight at the center. I'm going to just put it up here for bookkeeping. So this is equal to 20 times 9.81, which is 196.2. Okay, and now we have the two joints. So now we have to, now we can just go back and look for these types of joints and look at what the rules are. But a roller applies a force that's perpendicular to the surface toward the body. So this force is like this. And you could call that N or R or whatever. And then the hinge is an unknown force vector. So this is, I'll call that Rx, Ry, or I guess I'll just call it R vector.
Professor?
Yeah.
So because we're doing statics, and obviously you didn't give us things like the rowing friction or whatever, so any rower, it only produces it upward?
Right.
Only normal? Okay.
Yep. That's a frictionless contact. Yep.
The ruler's basically just there to keep it level, right?
Yeah, right. If it wasn't there, that thing would swing down.
Yep.
Okay, so that's a complete free body diagram. So now rho, force, moment. And for the about point, I'm going to put it here. So I'll start with R. The row vector for that is 0. The force is Rx, Ry. Cross product is 0. The weight force, the row vector is -1, 0. The force is 0, -196.2. The cross product is +196.2. The normal force is at the same spot as the weight. I'm ignoring the thickness of this, so anytime you're just not given thickness dimensions, it means just treat it like it's 0. It won't have much effect on the problem. So again, the row vector is -1, 0. The force is 0, positive n. The cross product is negative n.
Why do we have -1?
Because the rule for row vector is the vector from the about point to where the force is applied. So you start here and go there. So it's in the negative x direction. And the last one is the 300. So that row vector is -2, 0. The force, so let's think about this one a little.
Why don't we include the normal vector in the normal force in every free body diagram?
Well, remember that normal force is just, what it is a frictionless contact. Not everything has a frictionless contact in it. Like this one didn't have any version of that.
The normal force is when it's resting on something.
Yeah. Any frictionless contact, you can follow the rules of, pushing without friction.
Thank you.
Yep. Okay, so now we'll go, here's our vector. It has a magnitude of 300, and it makes an angle of 30 degrees there. And so my theta is, so start at the positive x-axis, go to 180, then another 30. So this is going to be 300 times cosine and sine of 210.
I was looking at the angle was 30.
I think I gave that.
Oh, yeah, sorry.
Okay, so so that's negative 259.81 and negative 150. So that's the force vector, negative 259.81 and negative 150. And the cross product here is 300. And so now I'll go to Newton's second law. And it says Rx, Ry plus 0, negative 196.2 plus 0n plus negative 259.81, negative 150 is equal to zeros. Rotational Newton's second law says 196.2 minus n plus 300 is equal to 0. So I'll write this as three equations. We have Rx is equal to 259.81. Ry plus n.
How did you come up with the rotational Newton's second law equation?
I just added up all the moments and set it equal to 0.
The moments are just the value of
those are the cross products that we got from that table.
Oh, the moment.
Yeah. So Ry plus N is equal to, that must be 346.2. And then the third one says N is equal to 496.2. So N is 496.2. And R, the X component is 259.81. And the Y component is 150. So the normal force, pushing forces can only be one direction, so it's good that we got a positive value there. These unknown components can be positive or negative, so that's fine. And basically what we see here is that force on the right needs to be kind of a mirror image of that 300 Newton force on the left for this thing to be in equilibrium, which when you think of it that way kind of makes sense that that has to be the case. Any questions? Yes?
For the exam, for the exam, so how is it going to be look like and what are the topics?
The topics are everything up through problems 1 and 2 in rigid body statics. And it'll just be like 4 or 5 questions, that can cover any of the topics from vector stuff, vector calculations, to okay, so vector calculations, particle statics, or that beginning stuff from rigid body statics.
Professor, could you scroll down a little bit?
And we don't have any note sheet for exam, right?
Right, I'll give you all the equations always. So, and yeah, you don't use notes. Yes?
Is it calculation?
It's all calculations, yeah. So nothing, it's not like the quizzes. It's all like the daily problems. Yes?
Can we use calculators?
Yes, any calculator. So yeah, bring your good calculator.
And we can use RF, right? Reduced
Yes.
row echelon form.
Right, yes. Uh-huh.
So in the problem we just did right now, if we were to take just a more extreme version of it, we kind of assumed that the center of the circle was in the middle.
Yeah.
What happens if we were to move it very close to the point of the 300 newtons, and the 300 newtons was also perpendicular? Would that just cause a greater moment along the point A, or would the position
Yeah.
of the center?
You're right that it does have an effect on those moments. It doesn't have an effect on the forces, but that moment equation changes. Yeah. Question?
You also write down that we use reduced row echelon in the first, or?
I can, if you come up with the equations and then give the answer, I know what happened, I mean, I just assume you can just get your way from there on your own, so you don't have to be too explicit about that. Any other questions? Okay, that's it for today. See you on Monday.